Okay, hi, and welcome to another video of me solving a Leetcode question. So today we're going to be solving Leetcode 137, single number 2. Okay, so given an integer array nums where every element appears 3 times except for 1, which appears exactly once, find the single element and return it. And you must implement a solution with a linear runtime complexity and use only extra space. Okay, so my first approach is to keep track of, say, like, first of all, we can say, like, iterate over nums and keep track of how many times they occur, right? And so we can then approach this with something like a hash map, right? So we can say, like, have a hash map mapping, say, like, mapping it into an int, where we map, say, like, the number to, like, the number of times it occurs. Given that, like, every element appears 3 times except for 1, and this input is always guaranteed that way, once we process, we can just iterate over key value pairs, and then return, like, the one with the number, with only count 1. So yeah, so for example, I just say counts equals to this for x in nums, and the time complexity of this would be O of n with O of n space. Because worst case is obviously, like, every value in the array has a key value pair, and you would have to, like, store that. And actually, it's not worst case complexity. Complexity is just O of n, because, like, there's going to be, like, n over 3, like, keys. So space complexity is also O of n. So this implementation would go as follows. For x in nums, then if x not in counts of x equals to 0, and counts of x plus equals to 1 for key val in counts the items. If val is 1, then we return key, and obviously if it's an invalid input, we return -1. Just for, like, a dummy placeholder, but since we're always guaranteed that the input happens this way, this part should never reach. So then if I run this, this works. So far the time complexity works, but the memory complexity is pretty bad because, because we must use constant extra space. So there are probably solutions that use constant extra space, and that's the part that we have to, like, figure out. So I'm just gonna comment all of this out. Oops. Alright, so to use constant, well, if every element appears 3 times except for 1, okay, so for example, if we have, say, like, an array of, say, like 2, 2, 2, 3, then we need to somehow know that 2 occurs twice, like 3 times, and if we only use constant extra space, something that we could probably approach is, say, like 2, 2, 2 is an array in binary of 1, 1, 0, 1, 0, 1, 0, 1, 1, right? So this means that there are going to be, like, if we only consider, say, like, the numbers with 3 in them, so in this case it would just be, like, 2, 2, 2, or say, like, the numbers with only 3 of them, and exclude, like, the unique one, 2, 2, 2, we notice here that the binary of 2, 2, 2 have, like, in the positions where they have a 1 in the bit, it's going to, say, contribute, say, like 3 of them, right? And so what occurs here is that, like, if we only consider stuff like that, 2 through 2, and let's just say like 7, 7, 7, so in this case, binary would be 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So in, say, like a certain bit position, since we're only focusing on like numbers that have like 3 of them in the array, what happens is that like the total number of ones in the array, considering only these, will always be a multiple of 3. And we see that because say like every number either has a 0 or a 1, right? So if it has a 0, it's not going to contribute to, say, like the number of ones at that position throughout the entire array. And if it has a 1, there's always 3 of the number in it, right? So the number of ones in the entire array is always a multiple of 3. So for example, in this array, in say like the third bit, we see that it's 0, 0, 0, 1, 1, 1, because 7 occurs 3 times and has a 1 in the third bit. So it occurs 3 times. The second bit, for example, 2 has a 1 in the second bit and it occurs 3 times here. 7 also does as well. So this occurs 6 times. The first bit also occurs 3 times, because the 1 occurs in 7, but 1 doesn't occur in this, right? So we can also see that this is always a multiple of 3. So what that does mean is that if we do have, say, like an extraneous number that occurs only once, like say for example, let's just say like 8 or 5. Yeah, let's just say 5. So then the binary of that would be 1, 0, 1, right? In this case, we would see that the addition of this number in the third bit would mean that, like, say, the third bit occurs 4 times, and since it is not a multiple of 3, we know that, say, like, the number that only occurs once contributed a 1 in this position, and it made it not a multiple of 3. If we see that then, for the second bit, it's still a multiple of 3 because it's a 0 here, then it means that the number must have a 0 at that position because it did not, say, like, break the multiple of 3, right? Similarly, first bit now becomes 4. So that kind of gives us a general algorithm where we keep track of, say, like, the total number of occurrences of ones at certain respective positions. So our algorithm becomes as follows. Iterate over every number in the array and iterate over ith bits. Keep track of, say, like, the total count of ones over the array at a certain for every bit position, right? And then that means that then all we have to do is reiterate over the bit positions. If it's a multiple of 3, we know the unique number must have a 0 at that position. If not a multiple of 3, then we know the unique number must have a 1 at that position, right? So this means that the overall time complexity of this, first of all, is O of n, because we have to iterate over every number, and every number has about 30 bits. So it's like O of 30n or just O of n. Secondly, the space complexity in this case would just be O of 1 because we are only storing the count of ones over 32 bits. So it's just O of 32 or O of 1 here. So then, therefore, let's so then let's iterate over this. So counts for every bit so far as initialized with 0. And we're going to be iterating over 31 bits because like the integer limit is like 2 to the 31 minus 1. So then for every number, for and iterate over, say, like 31 bits. And we also have to check whether or not it has a 1 at that position. So we can do this by performing the left shift operator with the AND operator in this way. So if x, I think it's x left shifted I and 1, because what that happens, oh wait, no, it's x right shifted I, no, yeah, x right shifted I, because what that does is that, say like for any arbitrary bit, if we say like right shift by 2, what that does is that it will look at the 0, 1, 2th bit here, shift it all the way here, and if you AND it with 1, then it will delete every other bit except this bit, and if, say, like this bit shifted to the right is a 1, if you AND it with the 1, it will become a 1, so that tells you it is a 1 at that bit. Or if it is 0 here, 0 and 1 will be 0, and it will tell you that's a 0 at that bit. So that's why this works for checking whether or not the ith bit is a 1 or not. So if x right shifted I positions and 1 is a 1, then we know that we can increment the counts at I plus or equals to 1. Okay. So now that we initialize our counts, next part is to reiterate over these and see which one is a multiple of 3. So I'm going to say for I in range 31, if counts of I mod 3, that means that it's not a multiple of 3, and our number is going to have a 1 at that position. So it's going to be ans is equal to ans, or 1 left shifted I. And then we can finally return our answer. So, oh yeah, overall, counts is equal to, why is that? Oh. For this in range 31, for x in nums, for I in range 31, if x right shifted I, counts I plus equals to 1. I don't think I'm doing anything wrong, and so far it looks like it's accepted. So, ooh, wrong answer. Oh, we can also account for negative numbers, I see. But wait. If I iterate over this 31, why does this, okay, let's debug this test case and see why it doesn't pass. First of all, we should note that negative 4 I guess it's also a case where negative 4 can be then how are all of these resulting in negative 4s? Okay, so let's at least see what. Oops. I forgot. Like. Okay, first let's sort counts. That there. Oh. Oh, we should also iterate over that to account for the signs. Whoops. Still not telling me anything. I think it's because Python has that as, like, say, an unsquared integer, but binary of. Yeah, because it's stored in 2's complement, I need to do this. So that means that if is I should do 1, then is there a way to do this as signed integer in Python? C types. gonna see if that works. If not, I might need to... Okay, now it's accepted. And let's try submitting to this. Okay, now it beats time complexity. So in this case, we can get rid of the nums.sort that we use for debugging purposes. We don't need to debug this either. We don't need to debug this either. And if we run again, we should see that our time complexity is still pretty good. Hopefully it beats more than 10%, and our memory complexity should be fine too. Oh, wow. Wait, why is it still only beating 19.2? Counts to... Okay, just gonna delete everything that I don't need. I don't need to sort this. And counts for every number if counts of I plus equals to 1. I'm initializing this as cint. Yeah, wow, it's actually really bad for some reason. Let's try this approach with C++. Oh. So used to using vector and that I forgot how to use the normal array. So they translated C++. Oh. Oh. To use to Python and forgot about semicolons. Lovely. Okay, now it's getting wrong answer for some reason. Okay, so whenever I go to debug, it just decides to work all of a sudden. Okay, beats 14.24 time complexity. Memory beats 13.45, but you know what? We cook with it.